Everybody, once again, we're almost done with section. Or what I should say, chapter 1. What we're going to do today. By the way, I'm trying a slightly different program. Hopefully, you think this is maybe a little bit nicer. We'll look at section 1.4. This is going to be a very important section. Most of you have probably not seen this in a previous course. We're going to talk about trigonometric functions. Okay. By the way, I'm using a different recording device, so we'll see if this works out a little bit nicer. It's got a little bit different. You don't get to see as much. Okay, so here's the important things about trigonometric functions. There are 6 what we call trig functions. They are sine, cosine, cosecant, secant, tangent, and cotangent. I was on a good streak, but I ended up messing up the last one. Okay? Now, of these 6 trig functions, we want to be able to associate them with particular values. And the whole point is we're going to associate for a given right triangle some angle we are going to use the Greek theta almost always to represent an angle, and we're always going to utilize a right triangle. And so from this angle, you can see we call this side the opposite, we call this side the adjacent, and we call this entire side, which is the longest side, we call it the hypotenuse. Okay? Because it's the longest side. It's the one opposite the right angle, but we're always going to orient ourselves based on this theta angle. So the question is, for various values of theta, what do each of these 6 trig functions look like? So, we're going to start with the very first one. We're going to start with sine. Now, sine is usually, when we're talking about a function, we usually are going to just represent it as sin. We also have cosine, which we're going to represent as cos, and we have tangent function represented as tan. Now, what we want to do is we want to associate with each of these, going back to our right triangle, we want to associate various ratios for each of these values. So, clearly as I can be, the value of sine is going to be the value of the opposite side of theta divided by the hypotenuse value of the right triangle. Cosine is once again going to be a fraction, but it's going to be the adjacent side divided by, once again, the green hypotenuse. And finally, tangent is going to be another ratio, and it's specifically going to be the opposite value divided by the adjacent value. Which, as it turns out just from fractional notation, I will point out, this is a little less nice, but it is still true, that you can actually say it's opposite over hypotenuse divided by adjacent divided by hypotenuse, which can be rewritten as sine of theta divided by cosine of theta. Now, we don't really use this quite a bit. We really want to focus in on these three definitions right here. So for any given right triangle, we can always represent them using this idea. So let's get an example using an actual triangle. Now, another very important thing that we're going to have to notice, we're always going to associate these with right triangles. And for any values A, B, and C, there's something called the Pythagorean theorem, which was known well before Pythagoras' day, but he does get it named. Specifically, if we go back to our previous naming conventions, we can actually relabel our opposite, our adjacent, and our hypotenuse. And we can actually rewrite this as it will always be true for these right triangles that the opposite value squared plus the adjacent value squared is going to be equal to the hypotenuse value squared. And this is going to come in handy when we have to start defining some of these problems. Now, let's see an example that we're going to run into a lot. Well, we'll start off with a slightly easier one. Let's say we have a triangle that looks like this. First of all, is this a right triangle that can exist? Let's go ahead and ask ourselves, what is 3 squared plus 4 squared? That's going to be 9 plus 16, and that is 25, which turns out to be 5 squared. So we are good there. We don't have to necessarily worry about this not being a triangle that exists. Fun fact, I was helping my dad build a shed in his backyard a couple weeks ago, and the plans that he had written out, he needed a right triangle that couldn't exist. If we take some angle theta right here, we can go ahead and start talking about what some of these values are. So the sine of theta is going to be 3 over, the sine of theta is going to be, let me grab my eraser, the third value, or what I should say, the opposite value, divided by the hypotenuse. Cosine of theta is going to be the adjacent over the hypotenuse, and in this specific example, tangent of theta is going to be the opposite over the adjacent. Okay? So, as long as you can draw the triangle, most of the time that means that you can figure out exactly what these values are. We're going to get some values that we're just going to need to know. There is a reference for this called the unit circle, but we will get to that when we actually need that. Okay. Now, I want to keep these values up here. I'm going to get rid of everything else. Because as I said at the beginning, there's actually 6 trigonometric functions. Don't forget there's also cosecant. Sorry, I'm still figuring out how to use this program. Cosecant, which we're going to write CSC of theta. We have secant, which we're going to write SEC of theta. And then we have cotangent, which we're going to write COT of theta. Now, these are somewhat special in that, we only have so many combinations of opposites, adjacents, and hypotenuses. They're actually reciprocal functions of these 3 base functions, as I like to call them. So, Cosecant is just the reciprocal, let me write this word up here, reciprocal A over B goes to B over A. So, what is the reciprocal of sine? Well, sine was opposite over hypotenuse. If we flip that around, we're going to get hypotenuse divided by opposite. We can do similar things with secant and cotangent. Again, if we switch them over, we'll get adjacent on the bottom versus the hypotenuse on top for secant. And then when we go to cotangent, we're going to put, oh, didn't change my color. We're going to put the opposite down here, whereas the adjacent comes up. So, real quick, if sine of theta was, in our previous case, 3 over 5, what does that make cosecant theta? Well, it's just the reciprocal. It's going to be 5/3. So most of the time, we're going to talk about these things in terms of these 3 beginning basic trigonometric terms. In reality, you can think of tangent as also being constructed from sine and cosine. So really, sine and cosine are our building blocks, but we also might be more interested in the 4, 5, and the 6. Okay? But ultimately, we should start thinking about it. The ones that really, really matter, I think, are the sine and cosine. And you know what? I want to include tangent, so we'll go ahead and include tangent as well. Okay, now, what we've seen so far is a lot of just moving around, making sure that we understand what they are. If we define some different circles, we can get some different sines and cosines. But the real question is what questions can we utilize sine and cosine to answer? So the first thing is we want to take a look at them as functions. Okay, so sine of x, let's say f of x, is sine of x. What is that going to look like? Well, as we go through, we're going to see this periodic, and it goes on forever, that as x continues to grow and grow, it's like we're traveling on this wave. We're going out, we're going in, we're going out, we're going in. And we can label some important pieces. So first of all, we have something that in these functions we like to call amplitude, which is going to be the distance that it sort of gets perturbed, is one way you can think of it. It's like the heights that it gets to. And notice that amplitude is exactly equal everywhere. No matter which troph or peak you choose, these are all going to be the same for us right now. Okay? Now, there's also something that we call the period, or the periodicity, which is going to be the distance from peak to peak, or from trough to trough. And we want to be able to recognize for a given function what are its amplitude and its periods. Okay? We will later on discuss the unit circle. That's something that will come up. But right now, we just want to focus in on this. So, for, or what I might call the base functions, for base functions, sine of x and cosine of x, sine of x has an amplitude equal to 1, and it has a period equal to 2 pi. Now, it's very important that you recognize that I am not describing these angle measurements in what we would call degrees. I'm doing it in terms of what are referred to as radians. It turns out it's just a little bit more fundamental of a measurement. What are radians? Okay. We're going to go to the unit circle now. Specifically, we know that if we take a circle whose radius is equal to r, we're going to wrap that radius, that distance. This is where my tracing is going to come in handy. We're going to trace that distance around the circle. Now, in a perfect world, this red line here and this red line here would have the exact same. I'm not a very good artist. But the important thing is that the angle theta that goes around one radius length, when you connect it, we call that 1 radian. It's the specific angle that you would make starting from the x-axis that you would open up such that if you were tracing it along this path, you would trace out exactly 1 radian of the circle. Now, we know a full circle, the circumference is 2 pi, which means if we started here, let's go blue, and we traced out 2 pi radians, we would go all the way around the circle, and we would wind up exactly where we are. So, 2 pi is a full circle. In a weird way, 2 pi is acting like 0. And that's true for a lot of different cases where 2 pi represents the 0 case, and there's certain things that are true for 2 pi are also true for 0. This also explains why does sine and cosine have that periodic functions. It's because we're keeping track of this right triangle, but this right triangle is repeating. It's repeating here, and here, and here, and here, and here. It will repeat forever. That's why we have this periodicity. And that's also why sine and cosine have a 2 pi periodicity. Now, can we start to play around with them? What if we do something like g of x equals 2 sine of x? What is that going to do? Well, we're still going to get this behavior of this repeated line through space. But it turns out this number right here defines the amplitude. Notice, this is like the stretch in function transformation, right? Remember when we took something like x squared, or we did something like, we put a 3 there, we increased its value. Because it's periodicity, because it repeats, turns out this is going to give us an amplitude of 2. And it turns out it's the exact same for cosine. And I'll do a Desmos demonstration to help us. Okay? What about something like h of x equals sine of 2x? What happens if we put the 2 inside? Well, once again, we're going to see a change. But the specific change that we're going to see does not happen in the amplitude. We're still going to get these amplitudes of 1, but notice we just have way more peaks and troughs going on. In fact, we've shortened this period down to just pi. We're making it happen approximately twice as fast. Okay? We're stretching it. Or sorry, I shouldn't say we're stretching it. It's almost like a spring that we're sort of forcing in on both sides. Now, both those things together can give us our rule. If f of x equals a sine of bx or a cosine of bx, we know the amplitude is the value of a. I'm going to take another stab at that. We know the amplitude is equal to a. And the period, this one is the hard one. We start off with 2 pi, and then whatever that b is, we make sure to divide by it. Okay? So, amplitude is a, and the period is 2 pi over b. So if we get something like, I don't know, let's go 3 over 8 cosine of 3x. We know the amplitude is 3 over 8. And what is the period? Well, the b in this case is 3. We're going to do 2 pi over 3, which you might write as 2/3 pi. That's how long each peak and trough will be. So can we sketch this out? Sure, maybe. We'll go 3/8 up here. We'll go negative 3/8 down here. Now, cosine is a little bit different. Cosine actually starts at the peak and then starts. And we know what is the distance here and here is 2 pi over 3. That's the distance between those troughs. And it would also be the distance from this peak to this peak and from this peak to this peak. I didn't really technically draw it to scale. Okay. It's important that whenever we look at a trigonometric function, we also understand its amplitude and its period. Because once we know that, we pretty much have the value of it defined. Okay. Now, remember, sine and cosecant are reciprocals, as well as cosine and secant. That feels different. That feels, we want to put the co-word with the other co-word. These come from some very old language. These are all reciprocals. But, as we saw in the last lecture, there's something else that we can call inverses. Sine inverse and sine are inverses. And once again, we're using that power of -1 to represent the inverse. Okay? So, we're going to go back to our somewhat simple value, theta. Remember, we had 3, 4, and 5. This is a very basic triangle. And remember, sine of theta is 3 over 5. Now, what this tells us in terms of inverses, remember, we want to switch inputs and outputs. So sine inverse of 3 over 5 is going to give us theta. Similarly, if cosine of our theta is 4 over 5, what is cosine inverse? Well, apologies. Cosine inverse of 4 over 5 reconnects us to our original theta. So the idea is, whereas sine takes an angle as an input, and it associates that with a ratio output, sine inverse has a ratio input and an angle output. Same is true for cosine and cosine inverse. Same is true for tangent, tangent inverse. Same is true for all of the inverses. Okay? Trigonometric functions take in angles and spit out ratios. Inverse trig functions take in ratios and output angles. Now, we're going to run into a problem as we take a look at sine inverse. Okay. Now, at this point, I want to take you to the unit circle. I just think this is a really good. Picture to take a look at. So, the way that this works, this is the so-called. This is the unit circle. You're seeing for some specified angles, like pi over 6, pi over 4, pi over 3, you get these coordinate points. And the way that these coordinate points work is that we associate them with either the x coordinate is the sine, sorry, I'm having to use my mouse again, and the y coordinate is the cosine. I didn't think this through. I have to use my mouse for this. Okay. So, for example, what is the sine of, let's say, 5 pi over 6? Oh, goodness. This is absolutely backwards. Please don't listen to me. I was so concerned about the writing it. I wish I had never even written that. Remember, x is the cosine of theta, and y is the sine. I apologize for that. Goodness, this mouse is not very precise. Okay, what is the sine of 5 pi on 6? Well, the y value is 1/2, so sine of 5 pi on 6 is 1/2. Now, that is going to represent a problem for us. Why does that represent a problem for us? Because sine of pi on 3, no, I want to go back to the pi over 6. Sine of pi over 6 equals 1/2. But sine of 5 pi on 6 also equals 1/2. Coming from our discussion last time, not 1, 2, 1. Can we define an inverse? And the answer is yes. Reminder, x squared has the square root of x as an inverse only for x on the interval 0 to infinity. It simply is not, this function is not defined outside of this interval. We have to do the same thing for sine and inverse sine. Oh, by the way, real quick, this is a notation that you might see a little bit. If you ever see something written as arc sine, that's just a fancy way of saying sine inverse. So I might accidentally say arc sine. I'm going to try my best to say sine inverse. But if you ever see arc anything, just know that it's in trigonometric functions, it's defining an inverse. But it has it as an inverse only for x is going to be between negative pi over 2 all the way to pi over 2. Okay? So, in the same way that we have to restrict the square root function only to the positive numbers, we have to restrict inverse sine or arc sine to only being values between negative pi over 2 or pi over 2. Okay? This is going to cause some differences of opinion, but as a reminder, anytime that you utilize arcsine, it can only accept things negative pi over 2 or pi over 2. Those are the only things that it's allowed to use as its angle measurements. Or, I guess in this case, that's the only outputs that it will give. Its angle measurements are between 0 and 2 pi for sine. But arcsine only exists between negative pi over 2 and pi over 2. And this also makes sense. We're going to take a look at the graph, hopefully in a little bit, or I might have to make another video for that, because I realize my recording setup is not designed for it. We'll probably make a part 2 just to cover that. So, inverse sine is going to get restricted to negative pi over 2 to pi over 2. Now, this is also the bane of many a calculus student. Inverse cosine gets a different restriction. It's going to be restricted to 0 to pi. Okay? And this is going to change some of the angles that we might take a look at. We might get some differences of opinion. So if we try to find, let's say, the sine inverse of, let's go ahead and choose 5 pi over 6. Well, unfortunately, 5 pi over 6, not in our interval. So we have to ask ourselves, what is the appropriate interval for which we can do sine? And the way that I would look at it is we're going to go to the unit circle. And we have sine here and sine here, but we're going to have cosine here and cosine here. So, anytime that you're in one of these quadrants, so let's say quadrant 1, you're good. The sine inverse and the sine cosine are all defined on that interval. If you're in quadrant 2, the cosine is good, but the sine is, we're just going to have to translate to the right. We're going to have to translate it back to quadrant 1. Quadrant 3, we're going to move our sine once again to the right, but we're also going to move our cosine up so that it works. So whatever you're in quadrant 3, we're just going to take that, if we're trying to find the cosine of something in quadrant 3, or the inverse cosine, we're just going to match it up with the cosine of whatever's in quadrant 2. Similarly, we're good on sine, but for cosine, we're going to have to move it up. Okay? So when we look at something like sine of 5 pi over 6, we go to the unit circle. Here's pi over 2. 5 pi over 6 is right here. Okay? What we're going to do instead is we're going to say, okay, 5 pi over 6, we're going to move it all the way over here to pi over 6. I guess I should put that down here. And whatever this sine value is, that one is in our interval. No problems there. It's in interval. Okay? So, depending on where you are, and depending on what you're looking for, we're always going to have to do this translations. Sines will go to the right, cosines will go up, is just another way of thinking about it. Okay? What if we had something like cosine of 11 pi over 6? So again, we go to the unit circle. Here is 11 pi over 6. I'm trying to write that as neat as I can. We're just going to go straight up to right there. Or maybe a better one, because that's actually kind of the same one. Let's go cosine of 3 pi over 2. Once again, 3 pi over 2, not in 0 to pi. and 3 pi over 2 is right here. So what do? We translate it perfectly up, and we say the cosine of 3 pi over 2 is the exact same as cosine of pi over 2. They have the same cosine value. So if you're doing the cosine inverse of something that is not defined in this case, in this not right-hand triangle, we're going to have to translate it upwards. Remember, sine goes to the right, cosine goes up. Okay, let's take a look at a problem involving some trig and some sine, cosine words. And the most important tip, always try to draw a right triangle. This is the most important tip I can give you. In pretty much every instance, you always want to draw some sort of right triangle. So the specific one I want to take a look at, this is coming from your homework. It's the cosine of the inverse sine of the term 3x. Okay? So first thing that we have to do is we have to draw a right triangle. And this is something you're going to happen a lot. Okay? Now remember, 3x, because it's being plugged into sine inverse, that is a ratio. Okay? And then, once we evaluate sine inverse of that ratio, we'll get an angle that we can plug into cosine. Okay? So, as a reminder, 3x is the ratio, sine inverse is the angle. So I'm going to go ahead and define that angle, theta. And specifically, the only thing I know about theta is sine inverse of 3x equals theta. Okay, well, what kind of triangle has sine inverse of theta equaling x? Well, what if we did the inverse of this thing? That would be sine of theta equals 3x. Okay, now remember, sine is opposite over hypotenuse, and that's 3x over 1. So I can say that for this right triangle, the opposite side is 3x, and the hypotenuse angle is 1. Now, what about this side? Do I happen to know what that is? Well, the sine inverse doesn't really tell me anything, but remember, we have the Pythagorean theorem, which says that this squared plus this squared equals this squared. So for right now, if you'll let me, I'm just going to call this thing a. And the Pythagorean theorem tells me that a squared plus 3x squared is 1 squared. Or a squared equals 9x squared. Oh, sorry. I jumped a little bit ahead. A squared equals, just moving something over and multiplying it out, we get 1 minus 9x squared. Once again, we want to take the inverse. What is the inverse of the square root? We're going to take a square root, 1 minus 9x squared. That I can replace with a. So, once again, reminder, my goal was to take the cosine of the inverse sine of 3x. And what I've managed to do is I've managed to write a right triangle where what is the cosine of that angle? Well, reminder, cosine, adjacent over hypotenuse. I now have the adjacent and I have the hypotenuse. And it turns out, I'm looking for some space to write something. I'm just going to get rid of this real quick. It turns out that the cosine of the inverse sine of 3x is the square root of 1 minus 9x squared over 1. And you can omit the 1, doesn't really bring anything to it. But the whole point is, no matter what trigonometric thing I'm trying to reduce down, you have to be able to write a right triangle to try and help you. That's the most important tip that I can give you for this entire section. Okay? All right. If you are looking for a unit circle, for the record, I think Wikipedia has a great unit circle. And it also has some good trigonometric terms, just to kind of go through them one more time. Remember sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. We have cosecant, hypotenuse over opposite. Secant, hypotenuse over adjacent. And cotangent, adjacent over opposite. One more piece that you're probably going to want. Of course, we have the inverse operators. Reminder, sine inverse goes from negative pi over 2 to pi over 2. And cosine inverse is 0 to pi. Okay, I will post a follow-up video to this one that talks about a little bit more in depth on some graphing, some things. We're going to go a little bit more into the amplitude and the period, just so you can get a good idea of it. But as a reminder, if you have any questions, send me an email. I'd be happy to let you know exactly what I need, or let me know exactly what you need, and I'd be happy to do my best to get you that. Have a wonderful rest of your days, everybody.